Okay, hopefully you're all back after a break, and you had a chance to try out this exercise, which is to change all the elements with values 7, 8, 10, and 11 in matrix M using a slice, where matrix M is defined here as a two-dimensional matrix with 4 rows and 3 columns. And you can see here my attempt at doing this is producing something called mySlice, which is a variable but also a view onto a matrix, where I'm looking to see the bottom right hand corner. I want to get 5, 6, well, I want to get 7, 8, 10, and 11 down here. And so that means I need to get these last 2 rows, so row 0, row 1, row 2, and row 3. For Python indexing, that's 2:4, so that means 2 and 3, but finishing before you get to 4. And then here I want to get columns 2 and 3 here, which in Python indexing is 0, 1, 2, columns 1 and 2. So I want columns 1 and 2 and rows 2 and 3. And that equates to 2:4. So take this row and then finish before the next one. And then here columns 1:3, which means take this column and then this column. And that gives me this bottom corner down here. And then I can use that to update the those elements. And I'm saying here, set all of my slice, so all the elements of my slice equal to 1,000. I could just update one element of my slice. And so if I update element 0, 0 here and set that to 2,000, it's going to be 0, 0 in my slice, but it should be this element here that gets set to 2,000. And we can see that this element here is set to 2,000. Likewise, I can set my slice to 2,000 here, and we can see it hasn't changed the array at all. And that's because what I'm actually saying now here, and this is where the Python dynamic typing can be slightly dangerous, is actually I'm not saying set all the elements of my slice to be 2,000. I'm saying change my slice from an array view into an integer variable. And so if I printed there, print the type of my slice down here, you can see it's a variable class int. Whereas if I say, oh, actually, I want to do all the elements of my slice, every element of my slice to 2,000, you can see that actually now it's an array. So what I could, you've got to be slightly careful in Python that you don't overwrite the variable by accident. That works. So hopefully that made sense for you. Then we can also do reshaping arrays. So we can take slices and views. You can also reshape an array. So here we've got an array A, which is actually a one-dimensional array, filled up with A range from 0 to 5, shape 6. But I can take that and turn it into a modified NumPy array. So I can reshape A, my NumPy array, to actually be a 3x2 dimensional array instead. So we've not actually changed any of the elements underneath, any of the values, but we've changed how they're indexed and how you would access them. So I'm allowed to reshape those things as well. Of course, if I tried to reshape it to something which is bigger than the array, then it's going to complain. It says modifying the shape attribute, not a copy, requires the size remains the same. So I'm trying to make something which is 10 elements big from something which is 6 elements big, and it doesn't like that. Likewise, if I do something that's too small, it doesn't like that as well. So it needs to be the right size, but I can create it to be the shapes that I want it to be. Not 2x6, sorry, 2x3. And likewise, I could also create a 1x6 array as well. And you can see that's done something slightly different. It's still made it a two-dimensional array, but the first dimension has only got one entry. So that's definitely possible. If you want to make your array bigger, then you can do a resize of an array. And so you can use a function called resize, and that lets me actually change the size of the array here. Resize the matrix, make it now a 5x2 instead of a 6 element single dimensional array. And you can see it's made a bigger array. It also seems to have created more values in it. So it goes 0, 1, 2, 3, 4, 5, and then it starts again 0, 1, 2, 3. So this resize takes the input matrix and then creates a new matrix of this shape and uses that input matrix to initialize it. And so if the new matrix is bigger, then it will, fill up the first entries with the input matrix, and then it'll start filling them up again. So that's a perfectly possible thing to do. But yeah, so if you resize it as well. It's possible to do to use a function called base as well. When you do when you look at matrices to see if they're a copy of each other, so that's exactly the same as doing print mat1 ID. Sorry, ID of mat1 and print ID of mat and print ID mat1 ID mat. So we're just doing different ways of again saying, are these arrays the same? Are they copies, or are they pointing to the same thing? So this base attribute is possible to use as well to say, is mat a copy of mat1, or is mat exactly the same as mat1? We also have a function called reshape, sorry. And this is a way of changing the array so in the changing the shape of the array, but not modifying the contents of the array as well. So shape can change it, but modify the contents potentially. A reshape won't modify the contents. So if I said mat2 equals mat1 dot reshape, so mat2 and mat1 are exactly the same thing at the moment. If I reshape it the other way around, we can see that we've got the mat2 then becomes a reshape of mat1, whereas if we try to do the shape, sorry, yeah, so whereas we could do the same thing by going mat1 shape, we can, sorry, just remembering my context here. So the shape attribute rechanges an existing array. The resize attribute and the reshape attribute can create new arrays from the existing array with different sizes or shapes. And so the reshape one is a restricted version of this resize one here, which doesn't do any copying or padding, but lets you change the shape of a function and create a new function from it. So if we did mat1 reshape equals mat2, get rid of this one here, and just run that again. Like that. And then we could say print the ID of mat1 and the ID of mat2. And we can see that they are different objects. Here they've got different shapes. So we've got two versions of this array, but we've done it without necessarily doing any repadding or changing of the data that resize can do. Now, there's all sorts of things we can do for manipulating arrays. So from flattening to splitting, concatenating, ravel, which means sort of interleave displays, tile, trim, mesh grid. So there's lots and lots of extended functionality for MATLAB, which is really quite nice. It means we've got good ways of manipulating the data. We're not going to go through these in particular detail, but it's probably worth, after I've finished this lecture, having a little play around and see, if you can take two 1D arrays with mesh grid and then turn them into some 2D grids, and or you see if you can, what happens if you use split or concatenate on a couple of arrays to see what happens. It's also possible to do more than just simple indexing on arrays. So you can do creating indexes from indexes. So we can create a indexes for rows and columns and then pull out all the data we want. So here's an example here. I've got a two-dimensional matrix with these entries. Then what I'm saying is actually I want to take some of these rows and some of these columns. So what I'm specifying here is I want to get 4 items from this matrix. The first item is from row 0, and the second item is from row 0. The third item is from row 3, and the fourth item is from row 3 as well. So we should be taking something here and something here. And then we're taking the 0, the second, the 0, the second element. So we should end up with 2, 0, 2, 6, 8. When we 0, 0, 2, 0, 2, and then 9, 11, not 6, 8. I took the wrong row there, the third row, instead of the fourth row. But yes, so we take in this element, and this element, and then this element and this element here. And that means this row and this element. So 0, 0 in rows and columns corresponds to here. 0 in rows and 2 in columns corresponds to there. 3 in rows and 0 in columns corresponds to there. And then 3 and 2 corresponds to here. And so it's possible to pull out, views or patterns of data structures on the NumPy array. Now, it's worth bearing in mind that when we do this sort of fancy indexing, we're not creating a view, or like we do when we do slicing, we're actually creating a copy. So Q is, if we change P, Q won't update because Q is now a separate copy of that data. And so if we ran this here, we can see that if we update Q, we can change Q, but it hasn't changed the corresponding value in P because they're not linked together. It's just copied the data out outside. It's also possible to do what we call Boolean masks or logical expressions on NumPy arrays to get data through an index. So you can say, actually, give me all the values of this data where it's below 0. And so this is a logical expression here. M is below 0. M is the name of the array. So it's going to go through this and produce you all the elements that are below 0. So if we run this, we should get -1, -3, -5, and 10. And that's what we get here. Now, of course, there's an interesting question: is what is So if I then say z equals m0, and then I print id of z, id of m, we can see that this again is producing a copy and not a slice. So this is going and producing me a data set. So then if I say z of 0 equals 100, print z, print m, we've changed that 0 of entry there to 100, but it's not affected the original base data. Okay, and so here's a more complicated example, okay, where I'm creating an array from a range. So that should go from 0 to 9. That's what it produces. And then I'm creating another array, which I've called mask, but I can call that whatever I want. And it's creating an array of ones of the same length of my A array, but data type bool, so a logical data type. So you can see what that's actually created me is this array here, which is all true. And then I can go in there and set some of these elements to false. So I've set the first element, the third element, the fifth element to false. That's what I've done here. And then I can say, access my original array A using this logical array as a set of indexes, and it will only pull out entries where there is a corresponding true in this logical array. So you can see it's pulled out 1 because there's a true. It's pulled out 1 because that's the first true value, and then it's skipped over 2. So it skips 0, skips 2, pulls out 3, skips over 4, pulls out 5, and then gets all the rest because they're all the ones that align with true here. So you can do reasonably complex array indexing and masking and those kind of things, which is nice. NumPy also gives you sort of array operations where we can work on element-wise operations on the matrices without having to create loops to go through the matrices. And this is useful because it compiles down to efficient C or Fortran code, which is the underlying code has been sort of well optimized or vectorized, so it runs efficiently on the computer that you're using. So we can do what we call array operations, where we say, okay, we're going to have 2 arrays, A and B, and then I can do some operations. I've got A here, and I'm going to then multiply A by minus 0.1, and that's a single line, but that goes through and multiplies each element of this array here with minus 0.1. I could also have stored that into a new array if I wanted to. Now in normal Python, this line wouldn't get printed out, because we're in IPython. If we do an operation and don't assign it to anything, then it usually prints it out for us. We can also multiply, arrays together. So what we call pairwise multiplication here, where we can say where we're going to do the multiplication of 2 matrices together here, but it's not matrix multiplication. It's not the dot product, and so we can do the same thing down here using the dot function to do our matrix multiplication calculation down here. So NumPy lets us do pretty easily lets us do matrix vector operations, be it initializing the matrix to a certain value, or doing more complex functions on top of that, where we operate together. This is actually very much like what Fortran array syntax looks like as well. So it's quite nice in that context. There's a whole bunch of random number functionality built into NumPy as well. So you can do there's a random class which lets you do various random generation of data. So this is going to generate some random floating point numbers here between 0 and 1. We can also see what was a random integer will do. So if you remember in IPython, this question mark prints us out the help data for this doc string for this function. So again, you can see you can turn random integers from low to high. So obviously it's not going to be in the interval 0 to 1, but sort of 0 to something or low to high. And you can get it to just generate these kind of things. So we can see we can do, NumPy random int 2 size 10, and that will give you values from 0 to 2, not inclusive of a 2, so 0 and 1, and it'll give you 10 of them. So there's some quite nice functionality there. So again, here we're going to create a NumPy array, 25 elements between 0 and 4, because it doesn't include a 5. Going to keep 25 of them, and we're going to turn them into a 5 by 5 matrix, a 2-dimensional matrix here. And you can see we've got values of 0, 1, 2, 3, and 4 in here. I mean, it's also possible to use distributions for random number generation using a standard distribution here, where we can say create me a 2 by 2 matrix or from a standard distribution where the default is to have a 0 mean and a standard deviation of 1. So the numbers are generally generated within that range. Now, there's lots more stuff you can do in there. You'd have to go and have a look at the documentation for the NumPy library, and we can see if we look at the random number generator documentation, it says there's a set of utility functions and then a set of APIs here for all the different kind of distributions you can create. So we saw a normal distribution there, but binomial and exponential distribution and uniform and multivariate. And so there's lots of functionality built in for you. The likelihood is if you need random number functionality, then the NumPy library has what you need in there. Of course, that doesn't mean you don't need to take care using random number functionality to make sure that your random numbers are statistically random for your particular use case, as you always need to do. But there's a large amount of functionality already built into it. Okay, we can also create NumPy arrays from files, so data in files, and save NumPy arrays out to files. So we can process data, we can save data from our NumPy libraries. So here's an example where we're going to save some data first. We've got some random data and indexes for those random data. We're going to stack the data. So stacking means that we take these two arrays, X and Y, and then we put them together along the first axis. So we can see that we've, instead of having two one-dimensional arrays together, we've concatenated each first entry and each second entry and each third entry. So that's what the stacking function does. Of course, because these are floating point numbers, it's promoted the integers up to floating point numbers as well, so they're all the same type. And then we can save the data. So we can say NumPy save text. I'm going to save it as text. This is the thing I'm doing because I didn't save it to a variable here. I could have just passed a variable in here, but I haven't done. I can add a header and footer in, and I can put some kind of format in there. So if I run that now, that should have produced a file for me. And if I have a look what that file says, you can see it's added these comments in at the beginning and end, which is what my header and footer is. It's given you a format where it's actually taken those integers that were turned into floating points and turned them back into integers, because that's what we've specified here. Here's a format string which says I want a decimal, and then I want a floating point number with 1 digit before the decimal place and 4 digits after the decimal place. I then just save it to a file called save-data.txt. Now, of course, I could let me save this to a variable here. So let me save stack data equals this. And let's print stack data. And then let me set stack data of 2 equal to sorry, I am confusing myself. So stack data, what we're printing here, yep. So we can modify this. So you can see actually that I've changed this data here. So these are all numbers between 0 and 1, at least in the initial stack here, because you can see this is 8.2 but times e to the minus 1. Or e to the minus 4. Here I've changed this to 45, so that's 4.54 times e to the 10, well, times 10 to the 1. And then if I save that data, let's run that. So I need to save the actual data and not the thing. So let's save stack data. You can see that we can print out these values as well. So we can change it, we can print it out as a variable, and we can specify exactly how much data we want to print out there as well. So I could change that to 6 decimal places, and it will print out more data there. And so I can play around with that a little bit. I can then also load that data back in.
With the cell 150, if I try to run this command, the cat save data, I get the error cat is not recognized as an internal or external command operable.
So
yeah,
are you running on Windows there?
Yes, I'm running it on Windows.
Yeah, so that's because cat is a Linux command. Now let me have a look. So if you replace it with more rather than cat, does it do anything for you?
Yep, it helps. Thank you.
Okay, no worries. So that's nothing to do with Python. That's just passing on command here to the command line. And if you're on Windows, then it needs to be slightly different command, which is a good point. Thank you. So we can then also load the data back in, and we could have a look at what load text says actually. So we can see np.load txt. What's that telling us? Load text takes a file name, and then there's other things you can tell it here. But I'm not telling it anything else. I'm just letting it choose some defaults. But I can tell it things like, what's my delimiter? You know, is this comma separated data? Is it tab separated? Is it space separated? Does it have a header? And are there headers that we have to skip, like skip rows equals none? If I had a bunch of text at the bottom, at the top, I might want to skip it over. You know, what character am I using to tell you this is comment? So this is because comments is set to hash, it'll ignore any lines that got hash in it and all those kind of things. Anyway, I can load that data back in and print it out, and it comes back in the same form that I had printed it out in, saved it out in. We can also do, there's also this function called gen from text, which gives us even more functionality. It really does stress my bad typing doing this live.
Coding live is terrifying.
Yes, definitely. Why is it not liking my gen from text? Oh well, let me just get up the gen text. Yeah, okay, so that should definitely work. Gen from, oh no, that's because it's not from text, is it? It's from txt. And this should work. There we go. Got there in the end. I need to update this because this is wrong. Apologies for that. So gen from text gives you a bit more functionality to read in sort of more complex files. So you can skip headers, you can skip footers, you can delete characters, so you can sort of filter out some characters to ignore them and replace straight spaces and stuff like that. So so that's a more functional program to do that, where I'm saying, look, skip headers and skip footers and those kind of things. So you can see here, actually, I've not read into full data sets. So I've said skip headers 2 and skip footers 1, so I'm only taking a certain number of lines in from there. And it's also brought it in a slightly different format. So it's going to have brought it in class type float, which is, but not. So let's see what our print type p. Oh no, I don't want to do that. Print p dot d type. Float 64. So what have we got the same down here? Print p dot d type. It still brought it in as float 64 as well, but it's changed some of the representation of the data into more normal formatted float and integer data there. So that can be quite a useful function to process data you have and to bring it in. Now we're just about at the end here. There's obviously a lot more you can do with NumPy, but we don't have to. We don't have time to cover it in completely. We could teach a whole 3-day course just on NumPy and all the different functions and those kind of things. There's a couple of functions which you can use as well, NumPy save and NumPy load, which is shown here. And these are actually not just to load and save text files or external data files, but to save NumPy arrays directly to a file in a binary format. So it's in a more efficient, denser file format, but only something that NumPy will really be able to open and close. So if you wanted to save one of your MIPCs for later from NumPy, you could use NumPy save and then reload it with NumPy load, but it wouldn't be any use for, say, loading in text files or comma-separated variables or these kind of things. There's a bunch of functionality in Python which can be useful to work out whether things are quick or slow. And particularly when we start coming on to look at the parallel stuff tomorrow, we'll use some of these things. But one of the useful ones is TimeIt, which is a library where you can use, you can import it to time how long a function call takes or how long a line of code takes. IPython and the notebook actually gives you this %TimeIt, which can be useful for working out how long individual lines take inside your notebook here. So here's an example here. There are different ways we can access NumPy data, as we've seen, either using these square brackets or by using this tuple approach here. And the question is, are there any performance differences between from doing that. So what we've done here is created an array called ND, which is 100 elements long. It's a 2-dimensional array, 10 by 10. And then I've run an experiment with TimeIt here, which says run this for 10 million times, repeat it 3 times, and then just do this operation, ND55, so access this data entry 30 million times, and then do it using the tuple method here rather than the square brackets method over here, and see if there's any performance difference. And we can see here that actually accessing it in this format here, where we don't use multiple square brackets, but we use the tuple notation or sort of matrix indexing notation here, is faster. So we can see it's about twice as fast going in this way here than it is going in this way up here. And that's because this tells Python, NumPy here, to do some more, requires a little bit more work for it to index into where you want it to be compared to this approach here. So even within NumPy, there are ways of using it which will provide you better performance, and ways of using it which will provide you worse performance. You know, for instance, copying a large array from one variable rather than referencing it can take time. Now, if you need to do that, you need to do that. But if you don't need to do that, then it's something that's worth avoiding it. We also have an example here of using TimeIt inside a Python program rather than inside the NumPy or inside the IPython notebook. And so here you can see what you actually do is do the same kind of thing, but you can do TimeIt.timer, or you can actually do TimeIt.timeIt here, and then you provide the code you want to run as a string, and then run it as many times as you want, and that will do the same thing there. So we should just see exactly the same thing happening coming up here. So again, we can see we've got similar timings here. We've got min, max, and mean of about 3.25 milliseconds. Microseconds, 3.25 microseconds, I think. Oh no, 3.25 milliseconds actually, or 1.5 down here. So we can use this function here, which can be useful to explore the performance of our code. And you can see similar kind of things if we go up to large array sizes. So X is now an array size of 1 million elements. And we want to see what's the do we get the same performance of times in X by itself, or using X times X, or X to a power 2, so raising it to a power 2. So we can see that actually X times X is a little bit quicker than X squared. Over there. So there's different things going on here. And we can also have a look and say, well, okay, let's do the same thing, but let's do TimeIt for a set of ranges. What are we complaining about here? I'll need to come back and fix this. I'll have a look at what I've done wrong there. But so TimeIt is a very useful function for exploring the performance, both of functions that we write in our code and individual coding lines. Now, as with any kind of performance optimization of your applications, of course, what you need to do first is make sure your code is correct and don't worry about performance. But it's worth worrying a little bit about performance with NumPy, because the reason you've probably come to NumPy in the first place is to get good performance out of your Python application, doing large-scale operations on large-scale data sets. And so making sure that you're using Python NumPy in the most efficient way, once you're happy it's correct, is probably a sensible thing to do as well. So there's all that kind of functionality available to you as well. I'll go and have a look in a minute at what I've done wrong here and fix that. But that's sort of all we wanted to say in the first instance about NumPy. As I say, there's lots and lots of other functionality out there. There's really good documentation and examples. If we have a look at the NumPy website online, and go through numpy.org and go have a look. But what I wanted to leave you with now then is there's a couple of nice exercises down the bottom here for you to try and implement a couple of examples of doing using NumPy to solve some problems. So we give you solutions to these if you are struggling, but it's worth having a look. In this first one here, what we want to do is implement a Monte Carlo method to calculate the value of pi by sampling a space, sampling a quarter of a circle, and then working out how we do that here, whether a sample is within or without the outside the circle, and that should give us an estimation of pi. So what we'd like you to do is try and write a example which chooses a sample size, generates an array of random x coordinates between 0 and 1, generate, of course, of size n tot, this here, generate an array of random y coordinates between 0 and 1, and then count the number for which x squared plus y squared is less than 1, and that should be, we should be able to then use that to approximate the value of pi. So go and have a look if you can see that here using these formulas up here. And then if you are way ahead and you're doing fine and you want some extra challenges, then there are different ways of doing that as well. So one of them is to calculate using a Taylor series expansion, using a NumPy polynomial function, and so you can have a look at undertaking that operation down here, and we have solutions for that as well if you're interested to do that. So go and have a look at that. Let me know if you have any questions. I'll let Julian know if you have any questions. What we'll do is we'll do that until say about 3:15, or until everybody tells me they're finished. So once you're finished, you want to move on, raise your hand in here, or put a message in the chat. We can easily move on quicker if people are doing fine and not having any issues and are moving on fine with that. And then if we come back at 3:15, we can have a look at Matplotlib and start doing some of that, and then go into a break and then finish Matplotlib after the break. Are there any questions? Okay, just to fix the thing that I had broken here, this example here, where we've got some, either iterating over or doing the calculation directly, and so we can see here that we've got a for x in range size. This is a Python range, square the x. For x in NumPy a range size, square the x, or just do a NumPy a range and then square the result of that. And we can see actually the Python version, the pure Python range, is faster than the NumPy a range. It's obviously more overhead in NumPy, generating the NumPy a range. But actually, if we do this sensibly and we work directly on the array that NumPy generates, rather than iterating over that array using the Python for loop, we can get it much faster. So we can see that the vectorization, so when it goes down to the underlying NumPy and does all the functionality down in NumPy rather than passing it back up to Python, is a couple of orders of magnitude faster there. So a little bit of care in how you use NumPy within Python can provide significant performance benefits, particularly if we can stay right down in NumPy for most of the things we do, and we don't have to come back up into Python types and iterating over Python objects and these kind of things. So that's a good question. So these things down here, there's things at the end here telling you how many times TimeIt ran things to get my results. So now here I'm calling TimeIt, but I'm not specifying how many times to repeat things when collecting results. You can see when we ran TimeIt up here, inside the code, we were saying repeat things 3 times and repeat the overall experiment 3 times, and inside the experiment run this bit of code 10 million times. And that's because it's very hard to time small segments of Python or any code accurately. But if you run it many times, the same thing many times, and then time that large chunk of work, you get a much more accurate timing. So what we're doing here is TimeIt is deciding itself how long to run this for until it's decided it's got a accurate enough data set to be able to say what is the standard deviation of timings. And so here it said, well, for this one, it was a long enough operation, but I only need to run it 7 times. But I'm happy that I'm getting similar results each time I run it. Likewise with this one here, 7 times. This one down the bottom here, actually this ran so quickly that actually I want to run it 100 times, 7 lots of 100 times before I've got enough data to say I've got a accurate representation of a runtime of this. So it's just the variation of this TimeIt function when it's collecting the data, the timing data about the things it's timing.
Sorry, can I ask for help?
Of course.
Yeah, is it possible to share the screen? Or
that's a good question. Let me have a look.
We should be able to, but we need to make you a presenter. I can set it up if you want.
It's done,
okay.
I think. Try now.
Okay. Yep. Let me try. How can I, or where's the button to share it?
On the bottom right, there should be a box with an arrow in it, which says share content.
Mm-hmm. Okay, there we go. Mm-hmm. Okay, can you see my screen?
It's coming, yeah, I can see it.
Yeah, perfect. Yes, so this is the approach that I try to do. I generated 2 arrays with random numbers. Apparently they were all below 1, so I didn't bother too much and accepted it just. Then I introduced these 2 variables, and then I tried to run a for loop, and if the value
so this is not how Python for loops work, unfortunately. So what for I in X values does is actually give you back that X value brackets I.
I see.
If you want to do this, you want to do for I, comma index or for value comma I in enumerate X values
comma
I.
Comma I. Yeah.
So there's a enumerate thing you can do where you specify enumerate brackets. Let me see if I've got a sensible. Yes, so it's something like, let me put this in this chat.
Okay.
As well, just so you, something like that. I got it the wrong way around. The value and your I and your value are the wrong way around. But for I comma value in enumerate brackets x values.
Brackets.
And it's enumerate, I'm afraid, so it's not quite spelled right.
Oh, yeah, I see it.
Yeah, try that.
Okay. 4-0. Okay, yeah. It kind of goes in the right direction. Maybe I need just to increase the size. Okay, so there's something wrong with the below 1.
Right, so it should be, you've got below 0 rather than below 1.
Yeah, yes, that's okay, there we go.
So it potentially you need to also be careful about above and below, because you may be below, you may need it to be above or equal to 1.
Yeah.
I think it's possibly above or equal.
Above or equal to
1. And so also in reality, actually, you don't need to calculate this more than once. So you could say if x values squared plus y values squared is greater than or equal to 1, above equals above plus 1, else below equals below below plus 1. I think that should work. Yeah, so it's getting there. It's not quite right, is it?
It's not, yeah, but it's going to the right direction.
Yeah.
So let's see if I maybe increase the size.
I would have thought you're big enough there that you shouldn't. You should be okay.
Oh, now it's taking really long.
Yeah, it will do.
Okay, but yeah, I think that works now, right?
I think it's definitely there or thereabouts. Yeah, definitely.
Yeah. Okay, thank you a lot.
No worries. Okay, I hope you're getting on well with the NumPy exercise. If you need some more time to finish it off, that's perfectly fine. We have time after this lecture and the rest of the day. But what I want to do is just keep moving and get onto the Matplotlib stuff so we can finish that off, and then you can go back to the exercises if you require. So now I've moved, as you can see here, I've moved from core NumPy to core Matplotlib, and I've opened up this Matplotlib IPython notebook here, and we can see that this is discussing why would we want to use Matplotlib and how do we use it. So Matplotlib is again another library like NumPy, designed to provide effectively drawing and graphing functionality for Python. And so it's designed to make it easy to produce graphs and associated plots and make things that look reasonably nice quickly. So it's capable of both interactive and non-interactive plotting. It's capable of saving plots to files, but also displaying them to screen, and then letting you customize how you do plotting and how you do graph production, consuming data you've generated inside Python and generating graphs from the back of it. It's pretty closely integrated with NumPy, which means that you can use NumPy functions for reading data and then Matplotlib to display the data that NumPy has done that. So you can easily read in a CSV file into NumPy and write that out or print that out using Matplotlib. Now, of course, there's a lot more documentation. There's loads of things this can do. We're not going to go through all of them as with NumPy, but the website's pretty comprehensive from that. So what does Matplotlib do? It lets us have a quick look at data, produce a range of different kinds of charts from line graphs to bar charts to heat maps to geographical and map-based plotting, so it can do quite a lot. And it's designed to allow you to do sort of standalone scripting, a bit like GNU plot, within an IPython notebook and within IPython shell. And fundamentally, it works around this idea of a figure. A figure is sort of the canvas you're drawing on, and then you have axes, which contains an individual graph or an individual plot. And within that, you can have multiple axes with labels and titles and things that are displayed. And you can set this all up to, you can create a program which generates this, which means it's possible to do a really quite reproducible way of producing figures. Okay, so we can create a figure of an axis area. We can actually do multiple ones of those as well, and we can display it, or we can save it to a file. So Matplotlib has this file, this module called pyplot, which contains most of the high-level functions we need to do this graphing. But it is a very large library that can do lots of things, so don't get confused. Make sure that you're looking in the pyplot functionality rather than other things. If we look at Matplotlib, there are other parts of the API that can do different things, but pyplot is the place you want to start for the functionality we're looking at today. So what do? You can import Matplotlib, or you can with the whole library, or you can import matplotlib.pyplot, which is pretty standard. And as with NumPy, people often import it as NP. Here you can import Matplotlib as PLT. So this is pretty standard. So we can import NumPy, we can import Matplotlib, and we can import Matplotlib pyplot as plot. Now this special command here, we can see this has got a % sign at the beginning, so this is something that's going to the IPython notebook itself, and that's saying inline. So by default on the command line, Matplotlib will produce a new window with any graph it produces. We don't want it to do it here, we want it to display the pictures in this web page, so we're telling it to do those things inline. And so we can, as an example here, we're going to create a NumPy array called X and a NumPy array called Y, and these are going to be the data we want to plot. So if you print X and print Y, we should see that we've created two arrays, both with so the X arrays is sort of a linear spacing of points between 0 and 10. And the Y array are values using X calculated using the cosine function. And then we can just plot that pretty simply by using pyplot X, Y, so the two arrays, and then something here telling it how we want to display it here. So this special string at the end here, GX, means we want a green line, and we want green as the color, and we want to use X's as the points. I could change that and say I want dots instead by main GO, or I could say blue, blue plus, and that would let me play around with those kind of things. Now I don't have to tell it anything at all, and it will just produce a line if I don't do that. And if I just tell it a color, now there's a lot more complexity we can use here, but if I just tell it a color, I've told it to plot it in white, so it is there, but it's not being shown. So this sort of demonstrates the kind of power you can have. It's pretty easy to take a couple of arrays and plot them immediately, and I can then programmatically change how those arrays look. Now, of course, there's lots of things missing from here. We've got no legends, we've got no units, we've got no title, we've got no axis labels, but those all can be added in here. What we can have a look at is what the pie plot. Now let me see if this will work for me. Yeah, so the plot function will plot the coordinates of points or lines using x and y functions here. So what we've specified here is we've specified x is going to be the points along the x-axis where my y points will be plotted. Of course, I can actually leave off that x, just passing the data y, and it will plot my x and y, but not on the same scale that I actually generated them here. You can see it's done a default, there's 50 points, so each point gets an integer index all the way up to 50. Okay, so there's plenty of flexibility with the kind of data we're going to plot there. But there are also lots of other plotting functions as well. Okay, so you can see there's a lot of arguments that can be passed in here, things about the order of data, line styles, line widths, fill styles, dashes, colors. There's all sorts of things we can put in here, whether it's animated or not. So you can see there's lots of functionality that can be turned on here. I can also pass in these character strings which say, point, pixel, triangle marker, diamond marker, a standard set of color palettes, and these kind of things will go on here. Producing pictures in line is all very well and good, but in reality, most of the time we want to save them somewhere, and so Matplotlib lets you save file, instead of producing the data. Well, we've plotted the data, but we're also saving the data out to images. So if I do that here, you can see now if you're on Windows again, LS probably doesn't work, and you might have to do dir. But you can see that we've produced cos_plot.pdf and cos_plot.png, and there should be sort of two versions of my files here, which I can then use elsewhere. So just to let you get your hands dirty and get going to start with, what we want you to do is actually just plot some data from a file. We've given you two files here, random1.dat and random2.dat. We can read it in from NumPy, so we can do gen from text random1 and random2, and if I print them out, we can have a look. We've got two-dimensional data structures. This is data 2 as well, so we've got some different kinds of data structures here. We have two arrays. The file contains pairs of values which will be interpreted as x and y coordinates. Check what the data looks like, and then what we want you to do down here is plot data 1 using Matplotlib to appear as red crosses, and to do that we're going to have to pull out so we have to do some slicing in NumPy here to pull out the first index for the x-axis, and then do the same for the second index for the y-axis, and print them out. So have a go at that, see if you can produce, let me clear my cells down, clear all outputs. Have a go at that and see if you can get this data to be plotted up on a graph. We'll give you, well, okay, so that's nice. We've come up to the coffee break now anyway, or the afternoon break. So we'll take a break from now until 4 o'clock, and then we'll come back, give you 5 minutes then to finish the exercise, and then we'll continue and finish off the Matplotlib stuff as we go on. Any questions? So feel free to take a break, but if you want to keep going at the moment, we'll just want to do this exercise, plot data from file, all the way up to from here to end of step 4 there. We'll come back at 4 o'clock, 4 and have a look at this. If you're really struggling, then we've provided solutions for this as well. But give it a go and see how you get on. Okay, so we can get going again with the Matplotlib example. So here I've filled out some examples of how to plot these two files using NumPy and Matplotlib together. So from NumPy, we've collected the data sets using gen from text to get two NumPy arrays. And then you can see here that I've plotted my first Matplotlib figure with data 1, where I've created red crosses for each of the data points. And I've given it a label, but you didn't see this just yet, but that can be used in a legend later. So I'm saying my data for my X points are from the first column, all the rows from the first column, and my data for the Y points is all the rows from the second column. And so again, we're doing some slicing of the data here in NumPy, but let's just do that on the fly. And of course, I can play around with this. I could change these to blue points if I wanted by just changing the R to B here. I could change them to a different shape point using all the built-in functionality we have for that. And I could add a line to it as well. So if I put an arrow at the end here, not an arrow, a dash at the end here, then it adds a line as well as the point. And if I take the point away, I can just get the line and know. So I've got plenty of scope to modify Matplotlib presentation. I can do exactly the same thing with data 2. And then if I want to put them together on the same figure, then I can do this multiple plots at the same time. So I plot one, I plot the second, and then at the end I show it with both of them plotted on. So if I put the show in the middle here, then I separate out the two things into two separate graphs. But actually, if I do multiple plots together and then show the data, then I get a single graph with both of them plotted on it. And I can also add other things here. So I've added the legend in, and you see it's put the legend in at the bottom right. If I have a look at what plot.legend specifies, I can do labels and handles. So I can specify where I want the label, and I can specify the location. So I can put these kind of strings in here. There's all sorts of things we can do to specify where I want it. But if I went something like legend lock equals, I think this should work. Yeah, and lock equals. No, doesn't quite work, did it? Upper right, not top right. I can move around where this legend is. You can see this appearing here. There's lots more configuration you could do there. And I've also added an X label down here where it says points and a Y label up here where it says values. So that lets us do sort of pretty simple plotting from data sets quickly. This is exactly what was in the file here as well. This is the example from the exercise. Now there's lots of customization you can do as I've shown. We can specify the plot with different colors and different lines. So here I'm using cyan and a line, but I can change that color as we've already seen. And so we've specified in the figure size here. So I can do a 6 by 6 to make it bigger. I could do a 6 by 3. So I can change the size of the plot I produce by creating a figure and specifying that. I can also do figure sizes based on dots per inch rather than absolute size. I think I'm going off piste here, but let's see. Yeah, so dots per inch lets us specify sort of the resolution of a figure rather than the explicit size. And that can be useful when you want to save out high resolution images to files to use elsewhere. And then we can change as it's been shown here, the line width and the line size. So I can make thick lines, which also affects the points, or I can make thin lines like this. And I'm not sure what K is, but anyway, we can. Doesn't like E, doesn't like Q. Let's try O. Yeah. So there's plenty of different things we can do there. Now we can get more elaborate and complex with. Okay, there you go. K is the color black. Yes. Thank you. You can get much more elaborate with this, as we maybe see at the end. There's some nice things we can do to change. I'm not a big fan of the default color palette you get with Matplotlib, but there are things you can do to change the default color palettes to get something a little bit more pastel. And then we can also play around with marker size and marker fills, unfilled markers. And so if I change something like that, so this is marker number 1 or marker number 4, marker number 3, so it rotates them around, and I can change how big I want them to be as well. And of course I could say red or black. That's perfectly acceptable to do. And so those are unfilled markers. Those are markers which have no fill, yeah. And then we've got filled markers where we can do things like, you see there's an edge and a color, so we can have an edge color and an interior color for these kind of markers as well. So there's scope to do the outside as blue and the inside as red. So there's loads and loads of different configurations that we can do for this. And of course, you can imagine programmatically we can also do iterators over various markers. So we don't have to manually specify, you know, I want this marker for this plot, I want this marker for this plot. I can just say loading these data structures, iterate over a group of markers and assign them as sensible. We can also adjust axis sizes and axis scales. So here we can say we're showing X and Y, but we're only showing part of our data set here. So we're going from 0 to 3.14, and we're going from plus and minus 1. So we've moved our X-axis down from 0 down to well, okay, no, it was down there anyway, but we can specify where we put our X and Y axes. So we could change this to 10 as well, or just to 3, and so we can play around with the different axes we want to use. We can also do things about linear control, you know, linear or log graphs. I've just seen if we have an example of linear or log graphs. We can set a log axis if we want. To change those kind of things, so we can set a scale on the log axis. I'll look at the relevant code to do that and show you an example of that as well. So you can see we're now moving from a you know, pretty basic thing to something where we can add in titles in particular places, change fonts and font sizes and those kind of things here. So we can, we can put in an overall title, and then we can create an individual title and put where we want it, and we can move that around in the plot as well. So you can see we can move this place title from left to right. And we can also specify tick marks and annotations on the plot as well. Okay, so we can specify down the bottom here, instead of we've got an axis of numbers, we've now got an axis of these tick labels T1, T2, T3, T4, and we've created them in the particular range based on a linear space of xmin and xmax. So it's going to map these to various places. And of course, we can change the rotation and presentation of these. So we, if we've got large labels, we can make them up and down. So there's loads and loads of functionality that we can get in there. We can change specific annotations. So here we can do right on our Matplotlib plot. So what we can say is add some text in, add in an arrow, and say we want the arrow's location to be. We can say the size of the arrow, the width of the arrow, and the color of it, and then we can manually specify what we want to do on this. So there's lots of functionality there to let us take data and modify the graphs ourselves. It's also possible to do subplots in Matplotlib, so we can actually plot multiple things at once inside the same figure. So we've got a figure, and then each one of these boxes, what's called a subplot, is also an axis. So these subplot axes here, shouldn't have double-clicked that. And so we can get access to them with different subplot tuples to get access to each one of these here. So we've got number of rows and number of columns, and then that gives us a layout where we can change each one of these individually. So here's an example. We've created a 4x4 figure where we've got 4 different data sets here, and that creates us 2 objects. One is the figure, which we can use to change overall data about the whole plot, and the other one is the axis, which lets us change individual graphs. And you can see here now we're starting to plot, one graph on one of the axes and another graph on the other axis, and we could add other ones in here as well. So if we want to add a third graph, populate one of those empty ones. So we can say 0,1.plot. We're going to plot the same data, x and y, but we're going to plot it just with blue crosses, like that. And then on the bottom right, we could do, bottom left, should I say, we can say axis of 1, 0, dot plot x, y, and then we can do red crosses. Now, of course, in these examples are pretty straightforward. You wouldn't generally be doing this for things where you're repeating it particularly. But now the question is, how do I make can I remember how you make these different resolutions? And I can. Let me just check the specific syntax for doing that. So if we wanted to make our, will it do? It gets a little bit more complicated when you're using sub-figures, subplots. So let me just check the exact syntax of this. Again, I shall have to come back and look at in a little bit more detail. It should be possible for us to change the individual size of these different figures and the individual dots per inch overall of the figures. And I cannot remember at the moment the exact syntax to do that. So I'll look that up when you're doing the next exercise and add that back in. Okay, there we go. So you can do it with this overall approach to change the dots per inch for the whole figure, but it seems to need it to be reloaded, I think, when I run it. There we go. So it just takes a little bit of time to update in this notebook. So you can specify different resolutions as well. Now, it's also possible to do different resolutions for not just the overall plot, but the individual figures, but then we start getting a little bit more complicated. Okay, let me just punch that up. Yeah. So the notebook here is great, but sometimes it does have some little quirks, like things don't get fully updated every time you run the cells. It's also possible to spread these plots out, so we can see we can adjust the subplots to change their width and height spaces, so we're moving them apart. So if I change that to 1 and 1, we can see we've got a bit more white space between these different subplots here as well. And so it's possible to do quite a lot with these kind of things. So you can have a full control using a function called subplot to grid, which lets you specify shapes and locations, so you don't have to just have these regular 2x2, 3x3, 2x3 axes, but you can do something more complex where you have spanning figures and horizontal and vertical spanning figures as well. So we've got an example down here where we take a subplot and we want to create something that's 3x3, and then we specify individual parts of that subplot as being spanning various parts of that. So we've got a subplot with a certain size, and then we're setting our first graph is going to be the top left of that subplot, and the second graph is this green one here, which is top middle, but it spans 2 columns, and then the third one is starts middle left and spans 2 columns and rows, and then etc. etc. So we can start to specify particular ranges of things here. Now, if we add in a fifth one, which actually overwrites some of the existing plots, then we have some problems there. Let me just add in axis5.plot so you can see exactly what it is. Y, X, what color shall we give it? Let's go K plus. So it's created this graph here, but because this graph here overwrites one of the ones that was before, particularly axis 3, then it gets rid of it. And so we need to be experiment a little bit and play around to make sure that we don't get rid of some of the things. Likewise, if I plot something here, axis 5, which I've not created on this subplot grid, then it won't appear as well. But you can see the flexibilities here to do more complex graphs if you need them. And again, we may want to move these things slightly apart so that we don't get so much overlap between them. We can see the axes and we can do some of that stuff as well. Okay, so what we would like to do for you for the next 10 minutes, 5-10 minutes, is try and create a plot using subplots, which looks like this. So we want to get you to get something with this pie chart on the top, then these bar charts in the middle and bottom. And you can, if you follow these steps, you want to first generate a pie chart using arrays with 4 percentages as shown, and then 2 histograms from some data we already have here in the files. So we have this uniform data, and we have this one of these random data, I think, what we're going to use. No, uniform data and normal data. So read both of those in as NumPy arrays. And then we want to plot them in a 3x1 subplot, so you can get all the graphs to appear at the same time. And then once you've done that, if you can add in the labels and the axes and the legends and all those kind of things to get them looking nice. So you can start doing that here in this cell here. I would start off, just create the pie chart, see how you get on, then create these two separately, and then see if you can put them all together in a subplot. And we'll give you 15 minutes to try that out, and then we'll come back and finish the lecture in a second. Any questions, just let me know. Okay, so we'll just finish off this Matplotlib session now. So this is an example of what I did to create these graphs. It's a bit more of an involved exercise, this, because you actually have to create each one of the graphs differently, and we've not really been through the graphs you're creating here. So we created a pie chart and 2 histograms, and I've not shown you how to do that. But of course, the nice thing is you can go and check the documentation of examples that Matplotlib have online. And you know, you can start to see some of the idiosyncrasies of some of the different data structures or plot formats here. So a pie chart has some different features to a histogram, but some of the things that are sort of common across them, so labels and the data structures you want to plot. And so we can see here that to try and replicate this graph exactly here, we had to do a little bit more involved things. We had to rotate the starting angle of the pie chart. We had to set up the percentage printout, so the auto percentage. So we can turn that off, but we can also turn it on and specify what format we want in here. Interestingly, if we change it to a floating point number format, but a single point after a decimal place, or nothing after a decimal place, then it gives me these percentages: 15, 30, 35, 20. If I actually change it to a integer, you'll notice I get slightly different numbers here. So there's a bit of rounding going on here. So this is 34, not 35%, which is definitely interesting. And to actually replicate entirely, we had to play a little bit around with some dictionaries, setting properties of the actual graph wedges itself here. So we've got a dictionary here specifying the edge color and the line width. This isn't as nice as some of the other places where you can just specify edge color directly, but once you start getting into more complicated graphs, then these things have to start being passed in as dictionaries instead of directly as being set as parameters or arguments. And the histogram is a little bit simpler. You can see that we can do things like set the edge color. So if I take the edge color away, then by default, you see it doesn't give me any outlines between any of my things, any of my bins. You'll see if you actually go for the example that actually you can also change how you bin this histogram as well. So I think you can specify the number of the number of bins to use across the histogram. So we can change that to do some actual processing of the data as we display it as well, and that's definitely possible. So we can bin our data in different ways, and we can specify lots of other things going on here. So as I say, if you actually look at the example solution they've got here, they go into a little bit more detail on sort of labels of axes and this kind of thing. Now, the other thing that, of course, you have to do for this as well is specify the subplot. So I've got a 3x1 subplot, and then I have to specify where I'm putting things. So this function here, SCA, set current axis, lets me say, okay, at the moment I'm producing a graph, anything I plot to this axis, and then specify the next axis and specify the next axis, and then show it. So we can see we can do reasonably sensible subplots using this kind of functionality. There's also, lots and lots of other kind of plots you can use. If you have a look at the Matplotlib gallery, there's some really nice ones in there. You can also sort of start to specify things around setting up custom defaults for your Matplotlib. So you can have this thing called an RC file, where you want to specify, figures with certain colors or certain sizes or certain configurations. So you can sort of save some of your settings, and then what you can do is load them and do some kind of plots with our different configurations already baked in. So we can set things like font sizes, axis label sizes, marker sizes, and those kind of things. So you can do some pretty nice things there as well. You can also do LaTeX markup. So you can have LaTeX style text in your labels or your legends, which can be very useful for putting into papers. And we can also specify different rendering engines to do different kinds of plots. So, Matplotlib has this sort of a front end, but also the back end renderer. And there can be interactive renderers like we're using here, where it produces a picture for us to see, or non-interactive renderers which produce image files. And then there's different kinds of renderers we can use, which specify saving out to PNG files or SVG files or PDFs or PostScript files. So there's much more sort of advanced usage we can use there to improve exactly how we do things, or to unlock other functionality. I'm just going to have a look. There's also some quite nice things we can do with coloring, which I tend to, as I say, I'm not a big fan of the default colors for Matplotlib. So I quite like moving to a slightly different color palette. Let me just see if I've got an example of that kicking around somewhere. Give me a second. Yeah, okay, so there's some sort of slightly more involved functionality, or going into some of that that sort of functionality that we saw, where you can start to modify your environment. But if I do something like this one here, so plot RC parameters, axis property cycle, and then I specify a color cycler here, then I can change the default colors that we would get running through here. Now it's not working here because I'm manually specifying all the colors, but let's see if we've got this one here. If I turn off the colors, then we can see we can start to get slightly different color palettes to be used by default. So if I take away this plot cycler here, now it's not doing exactly what I want it to do. Give me a second and I'll sort this out. Well, I've successfully created them all the same color, which is not what I wanted to do. Yeah, okay. Doesn't seem to be playing very well with my NumPy notebook. My IPython, a Jupyter notebook. So I will figure out what's going wrong there and let you know. But there are ways to change the default color palettes, because plotting by default will go for a sort of fixed set of colors that it uses to create the colorscape and then move on from that. And you can change that to different sets of colors. So there's a whole range of different color palettes you can use for Matplotlib, from the default to the non-default. And so if I share this screen, you'll see that there are a range of different color maps where the Matplotlib will choose different colors from these by default. So you can see there's a whole bunch of different color maps and color plots that you can use to specify across your things. And so that can be quite nice to customize your individual plots using these two maps, and potentially also conversions to grayscales, which you may have to care about if you're running to put in things into journal papers, for instance. So you can see there's lots of complexity there in the kind of things you can do with customization of Matplotlib, and import some, generate some really quite nice functionality. If you want to have a play around, you can have a look at trying some custom configurations in your Matplotlib settings. Or just play around with having a look at some of the different kinds of plots you can do here, changing the histograms to other kinds of examples, and see what you can do there. But we've reached pretty much the end of today, so it's just about 5 o'clock here in the UK. So I'm going to wrap it up there. And if you've got any questions, do let me know. I'll go and work out why my color cycle is not working properly and fix that in the notes. And if you haven't got any questions, then feel free to keep going with the practical exercises, but we'll see you back here again tomorrow at 10 a.m. UK time. And thanks for coming along.